Christian Salvatori from Victrex. Presentation will be Victrex CT polymers for more reliable seal in cryogenic conditions.
How do I go on the presentation? How do I select my presentation? Okay. Okay. Hi everyone. So this is a presentation that I will give you today, which is on CT polymers, which is a new family of PEEK materials we have recently launched, and actually we have gathered in the last 4 years many data thanks to the work done with the processors and also with the valve manufacturers who tested the material. So we are today about to launch and fully commercialize this kind of products. So just a little bit, a few words on myself. I have started working in the oil and gas industry since the beginning of my career, either at Schlumberger, then passing by my friends here of Saint-Gobain, and now in the last 6 years, I am at Victrex as a business development manager for the EMEA region. So, who is Victrex and what do we do in energy? Well, we are, just to give you a few numbers, #1 experts of PEEK, actually because we invented PEEK 40 years ago already, and we have this only product. Actually, we don't do anything else than PEEK, so it's our sole focus, let's say. And when we have more than 40 years of proven performances in all the extreme conditions. So we always work to improve product performances, reliability, and OPEX, and also HSE, which is a quite trendy topic. There are 75 million seals. It's an estimated number, of course, but it's just to give you a flavor of how much PEEK is implemented today and is established as a solution for really extreme conditions, either in oil and gas, but of course in every other kind of market. So PEEK is known as a polymer for high temperature, typically, and also high pressure. So HPHT is the comfort zone for PEEK, let's say. But today we wanted to also extend the range of temperature of PEEK, having a material that can work also in the lower end of the temperature range. So today PEEK was specified to work down to -80 more or less, and now we have extended with this family of polymers, we have extended the range of temperature of PEEK by more than another 100 degrees. So the scope of this development was to create materials that can extend the range of temperature, offer a more reliable sealing, especially in cryogenic conditions, which is quite a challenging application, lower the torque, and allow cost saving, which is always important in this kind of industry. So the challenge here is typically non-metallic material, they have high coefficient of thermal expansion, they become brittle at low temperature. There are various ways to test cryogenic valves, and which are quite challenging again. And there are differential properties with steel components, because typically non-metallic material is in touch with a metallic material. And of course, it's really hard to have these properties matching. So what's the consequence of this? Actually, they tend to shrink, and shrinkage is something that who is designing seals doesn't really want, as well as who is designing valves. So you would like to have a stable material in terms of dimension, and as the temperature drops, they become very, very shrinked, creating problems in the functionality of the valve. And also they become stiffer and less ductile. And again, the sealing itself requires a certain ductility, because by definition, I would say, the sealing happens when there is a compenetration of a plastic part or non-metallic part with the counterpart, which is typically metal. So this is the challenge that we wanted to face by creating our materials. So if we start with the technical analysis, starting from the mechanical properties, we see that you can see here there is a CT100, CT200, and PCTFE. So CT100 is an unfilled grade, CT200 is a compound, and PCTFE is our benchmark. So it's the material we are competing against because it's the most used material when it comes to cryogenic valves. So we put these three materials in comparison, and as you can see here, there is a first analysis on the mechanical properties, specifically tensile strength and tensile elongation. You can appreciate a significant difference. So all these measurements, the major part of these measurements you will see are taken at minus 196 degrees, so it's in cryogenic conditions. And as you can see, either the strength and the tensile elongation are better, especially for CT100. So CT100 has an elongation of 8% almost at minus 196 degrees versus a 3% or a 4%. Okay, sorry, it disappeared. Or a 4% of CT200. So in this case, I would say CT100 has outstanding ductility because the elongation is can be somehow translated into the ductility of the material. So you have still a very ductile material at a temperature which is very challenging. It's almost minus 200 degrees, so it's everything really becomes a piece of metal. The modulus, it's actually really comparable. We don't want to have all the times better data, let's say. Sometimes we do, the most of the times I would say. Sometimes they are comparable. The important thing is that there is no worsening when we are comparing CT polymers with PCTFE. So in this case, CT100 is for sure really, really ductile. Also, in terms of impact, well, this was expected to have PEEK is for sure more robust, so you have a more robust sealing, and at the same time you have a more ductile material, either for both the materials, either for CT100 and CT200, compared with PCTFE. Compressive modulus, again, it's something very comparable, so there are no big differences between the compressive modulus of all the materials. But if we go on the thermal properties, actually here, which are very important, of course, for when it comes to sealing, we can see that CT100 and CT200 are lower and absolutely more constant. Now, the measurement here is taken from minus 180, more or less, up to 50 degrees. But you can think of having PEEK continuing that same trend up to at least the glass transition temperature, which is 143 degrees. PCTFE actually, it's not really linear, starts to grow, and it's not even usable anymore after 100 degrees or 120, depending on the pressure, of course. So you couldn't even get data, while for PEEK, you would have the same trend up to the glass transition, and even above, actually, it will stay far below the values of PCTFE. So this means that you have a material that actually all along the range of temperature stays quite stable. It doesn't really change its dimension as PCTFE does. And actually this is what you want, because also in terms of designing a seal, if you have a constant coefficient of thermal expansion, it's easier. So you have absolutely, this can be translated into reliability of a seal. Thermal expansion is really important. When it comes to thermal conductivity, this is also another property that becomes really important if seen in conjunction with coefficient of thermal expansion, because you want to have the lowest dimensional change possible, so a very low coefficient of thermal expansion in combination with the high thermal conductivity, because you will have a dimensional change, but you want this to happen as fast as possible. So the thermal conductivity in this case of CT polymers is higher than PCTFE. So you will have a reaction on the temperature changes of the material, which will be faster. And then again, it's again reliability, because if you have a sudden drop of temperature or a sudden change of temperature in a way, you will risk to have a transition, let's say a period in which the non-metallic seal will not be in touch with the metal counterpart, which will react faster. So it's again a way to say that CT polymers in this case are better than PCTFE. And just to go back on the thermal properties here, on the mechanical properties here, you can see that CT100 was the best compared also to CT200. So it was more ductile, more robust for sure. But when it comes to the thermal properties, actually, it's CT200 to be the best. So when to use CT100 or CT200, this will be clarified later on in a summary slide, let's say. But it's again, it's up to the valve manufacturer actually to understand what they are looking for, really, where they are struggling the most. Tribological properties. So the coefficient of friction is something also very important in the cryogenic application, especially in general, but especially in cryogenic application when you have this phenomena called stiction, which creates quite a lot of issues. And actually, PCTFE, in literature, we have posed the value of PCTFE coefficient of friction in 0.35, and it's not really performing. 0.35 it can be quite high sometimes, so you have to win a certain force. CT100 is actually comparable with CT200, so again, we have slightly lower values, but still in the same range. So there are no big differences between CT100 and PCTFE. And actually, this is another of the strengths of CT200, which is, again, a field material. So it has, it's lubricated somehow. And as you can see, I mean, this is a measurement taken at 5 megapascal. We also have the same results for 50 megapascal. So we wanted to simulate low friction and, a low pressure and a high pressure into a valve. And we got more or less the same results. So there is a significant difference between the coefficient of friction given by CT200 compared with the CT100 and PCTFE. So this is another point where CT200 is actually better again than PCTFE. Now, this is after we have gathered all this theoretical data, and this is back to 4 years ago already. We, in the last years, again, we started many testing campaigns, let's say, either internally and thanks to many valve manufacturers worldwide who tested the materials, because we wanted to translate the theoretical data into reality, into proofs. So this is just the first test we have made. We made the test comparing CT200 inserts on a side and PCTFE inserts on the other side on a 10 inches valve. It's a top entry, as per the Shell Mask 77300, which is one of the, let's say, which allows for the lowest leakage rates. And we made a TAT test starting from room temperature, going up to 120 degrees, then down to minus 196, and then back again to room temperature, with various level of pressure, of course, from 2 bars to 250, because it was a class 1500s, plus the 10% of the rate as foreseen from the testing protocol. So, and we have measured leakage, we have measured torque, and we have made an inspection, a visual inspection to determine the wear. Of course, we couldn't go further than 120 degrees because, as I said, there was PCTFE mounted in the valve. So it's absolutely impossible to think with this pressure to go further than that. And also, we made the same test reverting that curve. So not starting from the high temperature and then go down, but we also reverted just as an experiment, going before down and then up, because we didn't want to damage PCTFE or to compromise the capabilities, the sealing capabilities of PCTFE. And actually what we have measured here says that we had a lower leakage rate in every case, in average. I would say sometimes we had some leakage, but actually it's still acceptable and lower than PCTFE in all the temperatures. And also the torque, in average, is, if we normalize the PCTFE torque at 1, we can see that either at 2 bars, so low pressure, and 250 bars, so high pressure, in this range of temperature, we got a lower torque, which is, again, quite important. This is just one of the tests we have made. So we have replicated this test really many times. And of course, we had the chance to make the same test in various conditions. So in various range of temperature from minus 196 to plus 150. We made test on a 1-inch valve up to 24 inches valve. We made test from class 150 to class 1500s. So in every conditions, let's say, with several different kind of floating or trunnion kind of valves, we actually found these results. So we have built a certain confidence that these materials can really promise on and respect the theoretical data that we got at the beginning. So in summary, mechanical properties, higher strength, greater ductility, toughness and resilience, thermal properties, higher thermal conductivity, and more stable coefficient of thermal expansion. And regarding another advantage, if you want, PCTFE, it's a material that can be compression mold. We have given the possibility with CT100 and CT200 different forms to either injection mold, compression mold, but also you can spin cast, you can extrude, you can do everything. They are available in pellets, they are available in powder, they are available in micro pellets. So there are several forms and there are no issues in terms of processing the materials. Great comparison, just to have a clear picture of the differences between the two materials. Again, CT100 is for sure the most ductile material at minus 196, and it's tougher than CT200. CT200 has a lower coefficient of friction, either static and dynamic, and it has better thermal properties. So maybe it can be suggested over CT100 when you have soft steel balls, which typically happens like 316 for cryogenic valves, because it's known, unfortunately for me, that PEEK sometimes risk to scratch or create some scratches on the balls. So actually this is a material that avoids absolutely this kind of issue, which would lead to have a leakage. So CT200, I would say, it's for sure, as of today, the most requested. Let me spend a couple of words on hydrogen, just because, as Philippe said, it's an incoming trend, and everybody knows that there will be an energy transition that will bring, that will increase the demand of hydrogen valves. So this is just a sketch that you can find. There are thousands of these, the supply chain of hydrogen. So there will be phases where the hydrogen will be gaseous, and there will be phases when the hydrogen will be liquefied. And we are working on having materials, either CT polymers, but also we are open to study, and we are already studying some new peaks in order to minimize the leak and the emission, maximize the performances, and again, HSE is very important. So we are still in the phase of studying now how to get farther than this. So we really want to extend even more the capabilities of our material in terms of sealing capabilities. So the HHV of hydrogen, so it's a sort of measurement of the energy content in a fuel. It's of course lower for hydrogen than for hydrocarbons. So it becomes really important actually to minimize still even more the emissions and leaks and increase efficiency and maximize the reliability. So what we have measured, or the first property we started to think about was the permeability. Hydrogen can pass through everything. So we have measured the permeability of our material, either CT polymers and others, and we have noticed that actually it's lower than many other materials, PCTFE included. So either if you have gaseous hydrogen in this phase, or if it will be a liquid, we are studying either the CT polymers or other material. Permeability is for sure one of the properties you have to look at. And it's good to know and to say that PEEK has a lower permeability than other fluoropolymers or polymers. Coefficient of thermal expansion, as well as the thermal conductivity here, they will stay lower for CT polymers or for other peaks that we could release in the next future. We will have a lower value either for the thermal expansion and for the thermal conductivity. Of course, the curve will converge to zero as the temperature drops towards the 0 Kelvin. But we are still below the values, so it's still another reason for thinking of having a more stable material, a more reactive material. Testing program, we are at the beginning of testing our materials, as I said. So what we already got is tensile test at 4 Kelvin, and they are completed. So we already got the data of our peaks for this property. They are still quite confidential today, I would say, but they can be shared, of course, in case it's needed. The phase 2 is the future. So the next test that we intend to do, which will be still on mechanical properties, thermal properties, and tribological properties, as I've shown so far. But also anything else. I mean, we are investigating all along the supply chain. So actually, either with the processor, the component manufacturer, the valve manufacturer, and the end user especially, what will be the requirements? So if there will be anything else, any property to be measured to prove the quality of a good sealing in this kind of environment, we will be more than open to start a discussion and cooperate together to create these measurements. Again, so we are today addressing LNG challenges. We are also thinking ahead, I would say, about the liquid hydrogen challenges that will be even more challenging, sorry for playing with the words. And we want to cooperate and collaborate with every of you in the supply chain. So either if you are a processor or, again, an end user, to create materials that can address the challenges in the best way. I'm done.
Thank you. Thank you, Christian. Do you have some question for Christian?
Hello again. Are the CT100 and CT200 materials available in standard seal sizes that are commercially available?
Of course, because they are, as I said, they can be either compression mold or injection mold or extruded or spin casted. So you can have every dimension in the range of the typical sealing system. So from the very small ones to meters, if you want.
And commercially available, we could just order them.
Exactly, they are commercially available. CT200 it's still, but it's really something that will happen in the next couple of months, I promise. It's still with the provisional license, so it's still a development grade if you want, but it's actually, because it's just a matter of how many batches we need to produce to confirm, to have stable selling specification of a certain material. But it's really something, it's actually already sold in the world to valve manufacturers as well. So it's already, it's just a formal thing, but it's commercially available.
Okay.
It's commercially available.
Thank you.
So, hello, Alberto Seveso from New Way. Christian, you know, we qualify with test both the polymers, CT100, CT200, from in the last 4 or 5 years during the development. And I can confirm that we pass, for LNG valves cryogenic application, we was able to extend the range of application thanks to this material for CT insert. My question is more relevant to liquid hydrogen. How to understand how you classify the mechanical properties of the polymer. I want to do the same question at the previous speaker when with this FEA simulation, the characteristic of material is a base step to start the simulation. So my question is relevant where you check the properties at minus 253 and how to do this type of testing, because it's quite critical, or is just a prediction or extension from other properties at either temperature. So my question is specific on this point.
Yeah. Well, assumptions on extending the existing data, it's something we have to rely on regardless what we have in mind, because that's actually an empirical way to guess what will happen at minus 253 or 269. So, but that's not enough, of course. So actually, we are looking for laboratories that can make this kind of test, which are challenging and expensive. So we have some partners in Europe, but also actually outside Europe, that we are investigating with for understanding their capabilities. And again, as I said, we are also open to cooperate because we don't have the full knowledge of what a valve manufacturer would really wish at the end. So we need to, as we always done in past for many other things, we need to cooperate with you to make the things together. So it's something it's something really new, Alberto. It's something we are thinking. This 4 Kelvin test you have seen, it's from last month, and this is just the first one. So it's something we have to think on, but for sure, Victrex is open to invest on this. So it will be just a matter of understanding how to make this kind of test. But for sure, again, assumptions will not be enough to prove that. Also because for the market, peak in this kind of conditions, it's a new thing. So we have to convince the market with data.
So thanks for this, but there is the risk that we are in a loop.
I know, it's chicken and egg.
Because this is also for us is the bottleneck many times to validate our performance. But I believe the Victrex with the capability, so invented peak and something like that, should invest in qualify the material, the proper temperature for first basic mechanical properties, tribological, whatever, what is possible to do, and then develop the application together. So.
Which is not a fast process anyway.
Okay, thank you.
Yeah, if I just can answer my part of the question, because you're looking at me as well. I would join Christian on what he said. It's not a simple process. We did run tests in hydrogen, tribo test, tensile test in liquid hydrogen, both of them. And we're still running it because we have quite a lot of material, so we would like to qualify as many material as possible. And then the data that we're putting in our simulation database, they are real data. We are not then trying to expand the data or try to simulate something we don't have. The idea is to really be able to simulate something we did test it basically. And then in the end, the final application will always be different than the test we can do, because we can't test every single possible situation in the world, and that's where, as Christian said, we would need then your help to understand the system, see how close we can get to it, and then deliver a solution that would then be fitting your need and still have to to test in those conditions. That's an inevitable for sure.
So thanks for the reply. My specific point was for the liquid because it's really difficult to start.
Good morning. Andrew Hamilton from James Walker. Thanks for the presentation. Just a quick question for me, really, with the analysis that you've done and the testing you've done against PCTFE, and we know particularly PCTFE at the moment seems to be more difficult to get hold of in the marketplace. Do you have any intentional plans to assess CT 100 and 200 against some of the other materials on the marketplace, maybe from the polyamide type material base?
Thanks for the question. It gives me also the opportunity to talk about one thing I forgot to mention. So polyamide, for example, is one of the other materials used, but actually, really, from my experience, maybe you can tell me I'm wrong. It's like a niche, in a niche. So it's the 90% of the times it's PCTFE. That's why we have taken PCTFE as a benchmark. There can be modified PTFE sometimes, there can be polyamide, but actually we wanted to have, I mean, we couldn't test again against everything, so we wanted to take the best reference, and it was PCTFE. Actually, polyamide is times more expensive than PCTFE or PEEK or whatever other material. So it's really not a really preferred solution for valve manufacturers. The most of the times, if they really don't have alternatives, they go for polyamide, but actually if they can avoid it, they will. So it's, again, it was not a benchmark either because it's not really largely used, but also because it's super expensive. Also, the opportunity I have to on this topic is to say that PCTFE today is suffering of shortages, as you said. It's not, and also it suffered of price increase in recent months. So that's where it stands, the cost saving that also CT Polymers can bring. So directly, because they cost more or less the same in terms of euros per kilo, but PEEK has 40% less density than PCTFE. So instead of buying 10 kilos of PCTFE, you will buy 6 kilos of PEEK for making the same number of parts. And polyamide in this case, it's even, I mean, it's out of the market for ourselves because we are already 40% or 30% lower in price than PCTFE, which means 10 times, many times lower than polyamide. So it was not our benchmark, really.
Okay, thank you.
Jeff Lewis from DuPont. It's just to mention that the latest versions of polyamide that are used in cryogenic conditions are priced similar to PCTFE.
Very good.
You'd like to know?
I have to.
I have a general question for you. It's an interrogation, more an interrogation. Concerning the thermal expansion at minimum temperature, at low temperature, how do you manage the thermal expansion compared to the metallic part? Because generally speaking, we have to mix PEEK material with a metallic part. And this is a part from valve manufacturer, or you collaborate with valve manufacturer on this particular point?
Sorry, can you repeat the question?
How do you manage the thermal expansion at low temperature compared to the metallic part? Because we have to use your product in combination with metallic part, and you have dissimilar
of
thermal
course,
expansion. And
there will always be a difference, Christian, but actually we wanted to compare. You will use a metal part in touch, let's say, with PCTFE. So instead of using PCTFE, it's better to use PEEK, because PEEK has a lower coefficient of thermal expansion and a higher thermal conductivity. So I'm not, let's say, comparing metal to metal with metal to PEEK, but I'm comparing metal to PCTFE and metal to PEEK. And in this case, there are several factors to judge that it's better to use PEEK rather than using PCTFE. The comparison is with PCTFE. So instead of PCTFE, which will have worse properties, thermal properties, in this case it's better to use PEEK.
Okay, understand. Thank you, Christian. It's okay. No more question. Thank you.
Thanks.